virtual competitive algebra seminar. We are very happy to have Jason McCullough from University of Iowa State University, sorry, in Ames, and he will give two talks, interrelated two talks on Eisenbud-Goto conjectures and the role of reaslike algebras. Jason, you are welcome to begin your 1 hour talk, and we will have question answers at the end of the talk.
Okay. Well, thank you very much. Thanks everyone for coming, and thank you for the invitation. I've very much enjoyed watching the talks from this seminar, even if I don't tune in live. It's a little bit early out here in Iowa. A couple of things I wanted to mention first. Yes, this is the first of two talks, and I was asked to start with some basics. So I suspect the majority of the first talk may not be new to certain people in the audience, although maybe it will be new to some of them. If you want to look at references in the literature, so I put 3 of these papers that contain the bulk of the material in this talk. If you don't have access, they're all available on my webpage, so you can read about them there. In particular, this last paper is new. This is a survey paper that Irene and I wrote fairly recently about what's been going on with Eisenbud-Goto conjecture, what's been done, and what's still open. So the bulk of the talk is this joint work with Irene Peva, where we constructed counterexamples to the Eisenbud-Goto conjecture. But later parts of the talk will be joint work with Giulio Caviglia, Mark Chardin, Irene Peva, and Matteo Varbro. And then a little bit at the end will be joint work with Paolo Mentaro and Lance Miller. And it's my work with Lance and Paolo that are going to be the bulk of next week's talk, where I'm going to focus specifically on reaslike algebras and what we can say about them algebraically and geometrically. So let me get started. So first I want to describe the basic notation for free resolutions. So throughout, I'm going to assume that K is an algebraically closed field. Some things hold more generally, but this is easier to make this assumption from the beginning. S is going to denote a polynomial ring in n+1 variables that we assume is standard graded, meaning all the variables have degree 1. And I'm going to let S sub I denote the K vector space of homogeneous degree I forms, or degree I polynomials. And I is going to denote a graded ideal, say generated by M homogeneous polynomials of S. So that just means each of the generators Fi lives in some Sj. And I'm going to use X to denote the projective variety associated to this graded ideal, which then lives inside projective n space. So with this data, what you can do is you can associate a minimal graded free resolution. So I'm going to let F dot denote the minimal graded free resolution of the quotient over S. And I get to say the minimal graded free resolution because such things are unique up to isomorphism. And so if this is a graded free resolution, that means each of these Fi's is a graded free module. So I could write it perhaps as a direct sum over J of S minus J to a certain rank, say beta ij, where S minus J is really just a copy of S where I've shifted the degree. So the degree I part of S minus J is the degree I minus J part of S. So it is convenient, rather than to write down the full resolution, just to keep track of the ranks of the modules and which degrees they show up in. So it is convenient to record these beta ij's, what are called the graded Betti numbers. In a table that we call the graded Betti table. just the Betti table for short, where the convention here is that we place beta I comma I plus j in position I comma j. And there are several reasons for this. Maybe the most basic one is that because the resolution is minimal, all the entries in the maximal ideals, or all of the entries in the matrices that define the differential are in the maximal ideal, which means the degrees have to go up by at least 1. So if we didn't do this, you'd have one large triangle of zeros that makes for a rather inefficient picture. So by shifting, say, column I up I places, you've erased that triangle of zeros. And since the resolution is unique up to isomorphism, any invariant you pick out of the graded Betti numbers is also an invariant. So I could define, say, the projected dimension or the length of the resolution in terms of the Betti numbers as the maximum I, such that one of these beta ij's is non-zero. And then the other invariant that's important for the conjecture is what's called the regularity, which has earlier motivations in algebraic geometry, but in terms of free resolutions, you can define this as the maximum j, such that beta I plus j is non-zero for some I. Okay. The other bit of notation I need to set is regarding Hilbert functions. So I'm going to write hf s mod I of I for the Hilbert function. So this is just the k dimension of the ith graded piece of the quotient. And as you may know, this is eventually polynomial. Which is called the Hilbert polynomial. And I'm going to write HP for Hilbert polynomial. And in fact, you can say something a little bit stronger. Rather than just saying that it's eventually a polynomial, you can bound where the Hilbert function and Hilbert polynomial agree. So in fact, you can say that the Hilbert function and the Hilbert polynomial agree for I bigger than or equal to the regularity plus the projective dimension minus n. And in fact, this bound is sharp if the underlying ring is Cohen-Macaulay. Sometimes it's more convenient, though, to keep track of the Hilbert function by using its Hilbert series. So we call the generating function of the Hilbert function of S mod I, the Hilbert series. So what I mean here is I'll write HS of T for the possibly infinite sum, where the Hilbert function is the coefficient of T to the I, where T is just some bookkeeping variable. And this is convenient because this can easily be calculated once I give you a resolution. And once you know the Hilbert series of S and you know a resolution, you can compute Hilbert series in general. So this can be calculated from the Hilbert series for the polynomial ring. So I will leave this as an exercise to the grad students in the audience to check that the Hilbert series of just the polynomial ring can be written as the rational function 1 over 1 minus t to the number of variables, which was n plus 1. And well, once you know that, you use the fact that since k dimension is additive in short exact sequences, you can write the Hilbert series of the quotient as an alternating sum. So alternating sum means I need a -1 to a power beta ij t to the j over 1 minus t to the n plus 1. So I know that's a lot of notation if you're not familiar with everything, so let's work out an example. So I'm going to take, for my ideal, P to be the kernel of the following map. So S is going to denote a polynomial ring in 5 variables, say x0 through x4, mapping to a 2-variable polynomial ring. And so this is just going to be the map that sends these 5 variables to the 5 distinct degree 4 monomials in these 2 variables y and z. So y to the 4, y cubed z, etc., to z to the 4. So you may recognize this as what's called the 4th Veronese embedding. So v of p is a variety that lives inside P4. This is called the 4th Veronese curve, for instance, if you want to think of it that way. You can also think of this as a rational normal curve. So you can ask, well, what are the generators of this ideal? It's not hard to show that the generators correspond to the 2x2 minors of this 2x4 Hankel matrix of linear forms. So I2 just means take the 2x2 minors of this matrix. And if you resolve the quotient, in this case S mod P, this has Betty table. It looks something like this. So remember the way we index Betty tables, the columns correspond to the homological degree, the rows correspond to the graded degree modulo this shift. So the 1 here corresponds to the fact that I'm mapping onto S mod P, so I need a single free module. There are 6 quadratics corresponding to the 6 2x2 minors of this 2x4 matrix. It turns out that they have among them 8 linear first syzygies and 3 linear second syzygies. So that's the entire Betty table. So immediately you can read off from this that the projected dimension is 3, as that's the index of the last non-zero column. The regularity of the quotient is 1, as that's the index of the last non-zero row. And moreover, we can figure out the Hilbert series. So if you just use the resolution, you would write down something like this: 1 minus 6t squared plus 8t cubed minus 3t to the 4th over 1 minus t to the 5th. But of course, there's a more efficient way to write this, because you can notice that since 1 vanishes when I plug it into the numerator, 1 t must be a factor. So if you reduce this, this becomes 1 plus 3t over 1 minus t squared. And maybe I'll just mention here, you can check that the fact that this is a 2 implies that the dimension of the quotient in terms of Krull dimension is 2. So you interpret this geometrically as the dimension of the projective variety associated to it is 1. So you can then define the codimension of P, or the height of P, to be, well, I'm in projective 4 space. If the dimension is 1, the codimension should be 3. And you could also use from the Hilbert series that this means that the Hilbert polynomial is 4i plus 1. Okay, so if you need to have an example in your mind as we're going through this, think of this example, as this contains a lot of the complexities that we'll see later. The one last invariant I need to define is the multiplicity, or the degree. So this is the multiplicity of the quotient, which I'm going to write DEG, since geometrically this is called the degree, is, and there's three different ways you can define this in this setting. So first, you could define this as h of 1, where the Hilbert series can be written as h of t over 1 minus t to the d, and h of 1 is not equal to 0. So looking back at the previous example, we had the first way you would write down the Hilbert series using the resolution, and then you reduce as much as possible. So in this case, you could check that the degree is 4, because when I plug 1 into the numerator, I get 1 plus 3. Alternatively, you could define the multiplicity as the leading coefficient of the Hilbert polynomial. But you have to normalize this. So you have to divide by the dimension of S mod P minus 1 factorial. And so in this case, the degree of the Hilbert polynomial was 1, so I'm really just picking off this leading coefficient, which is again a 4. Alternatively, if you like to think geometrically, you can think of the multiplicity of the degree as counting the number of points of intersection between the variety, the projective variety associated to this ideal, and a general or random linear space of complementary dimension. So since the variety in the previous example was a curve and I'm living in P4, you take a random three-dimensional linear space and you expect to hit a finite number of points, and because the degree is 4, I expect to hit 4 points. Okay, so I'll just write down for here in the example, the multiplicity, or the degree, is 4. Okay, so we've defined all the players here. We've gone through an example, so it's time to state the conjecture. So this was a conjecture stated in a 1984 paper that has a lot of other interesting results as well by Eisenbud and Goto. So the setup is as follows. Let's let P be a graded ideal in an n+1 variable polynomial ring. I want to insist that it's prime, so the variety it's associated to is irreducible. I want to insist that it's non-degenerate. And algebraically, this just means there are no linear forms among the defining equations. Geometrically, this means that the variety is optimally embedded. It's not contained in some hyperplane. So this last part, you can just think that the first graded part of P is 0. So then the conjecture stated, if I'm going to state this in terms of the regularity of the quotient, this should be at most the degree, or the multiplicity, minus the height, or the codimension. And maybe I'm going to just point out here that in particular, this would imply that the regularity is bounded above by the degree itself. And even this weaker second inequality, where you ask, is the regularity less than the degree of the multiplicity, that was completely open at the time we worked on this problem. So let's go back and look at the example. So in the example, we said the regularity was 1. the multiplicity was 4, the codimension was 3. So we actually have a situation in which the bound is tight. And so let me just notice here that in the example, this variety is about as nice as it possibly could be. It's smooth. It is projectively normal, by which I mean the coordinate ring is integrally closed in its fraction field. It is arithmetically Cohen-Macaulay. And this is a curve. So let me just do a second example that isn't quite so nice. I won't do all the details here, but just take the same example, go back to our original map, and omit y squared z squared from the list of monomials. So then I'm going to be mapping a 4-variable polynomial ring to this 2-variable polynomial ring rather than a 5-variable one. So what you get is a different non-degenerate prime ideal, which corresponds to a projection of the variety we just discussed. And you can check that the Betti table of this new ideal looks something like this. So there's 1 quadratic and 3 cubics in the defining ideal, 4 first syzygies and 1 second syzygy. So you can read off here that the regularity is 2. After a little computation, you can check that the degree is 4 and the codimension is 2. And since the codimension is 2 while the projected dimension is 3, this is no longer an arithmetically Cohen-Macaulay ideal. However, it is still smooth. I guess I should write the quotient here. All right. And again, the inequality is preserved, right? So the regularity is less than or equal to the degree minus the codimension. So here's 2 settings where the conjecture does hold. And so let me now talk about what is known in general. So what are the known cases? There are many of them. I'm not going to have time to list them all out, but let me hit the sort of the highlights. So the conjecture is known to hold for all curves, so for all one-dimensional varieties. This is a famous paper of Gruson, Lazarsfeld, and Peskin. From around the same time the conjecture was made, so this is 1983. It's known for smooth surfaces over C. So this is really work of Lazarsfeld, derived from work of Pinkham from 1987. It's known for most, I'm going to put that in quotes here, since I'm not going to define what I mean, for most smooth threefolds, again over C. This is work of Zivran from 1990. And then I can remove the most and say all smooth threefolds, again over C, if you allow me to add a +1 to the bound. So instead of having degree minus codimension, you have degree minus codimension +1. So this is a result of Si-Jean Kwok from 1999. And he actually has a number of other slightly weaker bounds for higher dimensional varieties up to dimension 14. In their original paper, Eisenbud and Goto note that the conjecture holds if the ideal is arithmetically Cohen-Macaulay. And here they don't even need to assume that the ideal is prime. Just Cohen-Macaulay on the nose is enough. And there are many others that I don't have time to list, but if you look in some of the papers I mentioned, you'll see other references. So the big punchline is that, well, it does not hold in general, at least as stated. So this was my joint theorem with Arena-Pava from 2017, where we showed something actually much, much stronger. Not only does it fail, it in some sense fails very badly, in the sense that there is no polynomial bound on the regularity of S mod P, where P is a graded, non-degenerate prime ideal that is purely in terms of the degree. So remember, the conjecture, the weaker version of the conjecture predicted regularity was at most the degree, and so we're saying there is no polynomial in terms of the degree that bounds regularity. So in particular, conjecture is false, at least as stated. So this kind of leaves you with a conundrum of, there was this very nice conjecture, it was known to be true in lots of cases, it's something that deserves to be fixed, so how do you fix it? And there are sort of two obvious routes to take. Option one is to weaken the bound. And option two is to say that there were missing hypotheses that really should have been there. And I think both routes are worth pursuing. So let me first talk about option one. So this is in that joint paper I mentioned with Cavilli, Chardin, Pava, and Varbro. So we proved that there is a weaker bound, although we can't exactly tell you what it is. So if P is a graded, non-degenerate prime ideal, in a polynomial ring over a field, then there exist constants depending only on the degree bounding, well, everything in sight. So the projective dimension, the regularity, all the graded Betti numbers, of the quotient. The problem is this is a non-constructive proof. And the way we do this is we rely on a theorem of Ananyan and Hochster where they resolve Stillman's conjecture, which I'm not going to talk about today. But I'll just say that this problem is actually equivalent to a different problem that I'm very interested in called Stillman's conjecture, which basically asks, is there a bound on projected dimension irregularity in terms only of the degrees of the generators? And this is, of course, now a theorem of Ananyan and Hochster. And since they published their proof, there have been a couple more proofs as well, but they're all non-constructive. We don't have very good ideas for, either for this theorem one or for Stillman's question, what sort of the asymptotic growth rate for whatever formula bounds projected dimension or regularity, either of arbitrary ideals or in this setting for prime ideals. That's still an open question. So I'm going to write that down here. This is a question I'm very interested in. What is the optimal function, at least asymptotically, say capital phi of x, such that the regularity is at most that function applied to the degree. Right, so by our theorem, capital Phi cannot be a polynomial function. Could it be singly exponential? We can't rule that out. I think that would be a very satisfying answer. But at the moment, this is completely unknown. So that's sort of the most I can say about option number one. For option number two, well, there's still a lot of different ways you could go to insist that maybe Eisenbud-Goto conjecture is true if you just add that missing hypothesis. So what should the missing hypothesis be? Well, there are a number of options. So for option two, the conjecture is still open. In the following cases. So it's open in general for smooth varieties. It's open for, say, projectively normal varieties. It's open for toric ideals. Now I have to be a little bit careful what I mean by toric ideals. Some people, when they say toric ideal, they mean normal and toric, in which case you're automatically Cohen-Macaulay, and in which case the conjecture is true. So here I want to allow for not necessarily normal toric varieties. And it's still open for potentially singular surfaces. Oops, surfaces. So remember, Lossersfeld and Pinkham proved that at least over C, a smooth surface satisfies the Eisenbud-Goto conjecture, but for a singular surface, we don't know the answer. So, and these are sort of minimal in the sense that Irene and I constructed a three-dimensional, non-smooth, non-toric, non-normal counterexample. So all of these are still open. And there's also been recent work of Seizure and Kwok that implies that if you take the first two hypotheses, so if you're both smooth and projectively normal, the Eisenbud-Goto conjecture should actually hold there. Okay, so for the rest of the talk today, I'm going to talk about the construction of the counterexamples and what we can say about them. And then next week, I'll go further into understanding the algebra and geometry of these examples. So how do we come up with counterexamples? Well, let me remind you the notation here. I was supposed to denote a graded ideal, not necessarily prime, that had m generators living inside some, say, n+1 variable polynomial ring. Actually, I think I want to make this just an m variable polynomial ring. So we used something we called reaslike algebra. Let me first say something about Rees algebras, since that's probably more familiar to people. So what is the Rees algebra? So the Rees algebra of I is, well, you can write it as S adjoin IT, where T is a new variable. So this is living in some polynomial extension of your original polynomial ring. And people study this quite extensively, because if you take the scheme proj of the Rees algebra, this defines what's called the blowup of affine n space along the variety defined by this ideal. And so one of the interesting questions you want to ask, because this is an important step in the resolution of singularities, is, what are the defining equations of the Rees algebra? In other words, if I surjectively map a polynomial ring onto it, so let's take S and adjoin m new variables, map onto the Rees algebra by sending yi to fit, you can then define P to be the kernel of this map. And then you can ask, well, what are the generators of P? You know, what can you say about it? And at least in full generality, this is a very hard question. So in full generality, generators of P are difficult to compute. There are certainly situations in which we do know a complete answer. If P is a complete intersection, if it's a height 3 Gorenstein ideal, you know, certain cases like that we know, but in full generality we don't. So, you know, if you want to say anything about resolutions, if you can't even say what the defining equations are, that makes defining the resolution very difficult. So let's now define what we call the reaslike algebra. Of I is, well, you just take the Ries algebra and you slap on a t squared, which seems like a very unnatural thing geometrically, but algebraically it turns out to be quite nice. Now, I will fully admit Ries-like algebra is perhaps not the greatest name for this thing, but in our defense, truncated Ries algebra and extended Ries algebra were already taken, and at this point I think the name has stuck. So now, if I want to define the defining equations, I'm going to define a different polynomial extension of S, where now I need an extra variable z to map onto the Ries-like algebra. And so what do? We map yi to fit as above, and then z maps to t squared. And so then Q is the defining ideal. It's the kernel of this map. And even better, if we set the degree of yi to be the degree of fi plus 1, and the degree of z to be 2, then this is actually a graded map of graded rings, which means Q is a graded prime ideal. The downside is it's not a standard graded prime ideal. We'll have to come back and fix that later. So then phi and Q are graded, but not standard graded. So what's the benefit to thinking about Ries-like algebras instead of Ries algebras? Well, I claim that the defining equations and the resolution are very well understood. And so this is a part of the talk that I'm going to push off till next week. But let me just state here that unlike the Ries algebra, the Ries-like algebra has well understood defining equations and free resolution. So I'll say more next time on how to do this exactly. But as a result, Arena and I proved the following about Ries-like algebra of an arbitrary ideal without any assumptions. So let me go back and introduce some notation. I'm going to call this this ideal that maps onto the Ries-like algebra, or this polynomial is T, the new polynomial ring with S, with y1, ym, and z. So first of all, we can define the regularity of this new defining ideal of the Ries-like algebra in terms of the regularity of the original ideal with a couple correction terms. So +2 plus the sum of the degrees of the defining equations of I. Number 2, the projective dimension becomes the projective dimension of the original ideal plus the number of generators minus 1. the multiplicity, or the degree, becomes 2 times the product, I equals 1 to m, of the degree of the fi's plus 1, and number 4, the codimension of Q is exactly m. Now, there's a subtlety that I'm sweeping under the rug here in that what exactly do I mean by regularity? Remember, T is not a standard graded ideal, so in theory, I shouldn't be defining regularity in terms of resolutions. However, I'll show how to fix that later so that this really is an honest way of defining regularity after we do some homogenization. So I'm going to sweep that subtlety under the rug for the moment and come back and address it later. But a couple things you should note. So notice, remember, your Cohen-Macaulay if and only if the codimension and projected dimension agree. So the only way that this number and this number agree is if the projected dimension is 1. So T mod Q is Cohen-Macaulay if and only if m is 1. So in general, reaslike algebras are not Cohen-Macaulay except in the case when they're going to be a hypersurface, and I'll show you an example like that next week. Also notice it's very easy to tell that this is never normal. For instance, T is in the fraction field of the reaslike algebra. But not the reaslike algebra itself. And it's a root of x squared minus t squared, which is a polynomial over the reaslike algebra. So this is not a normal ring. It's not integrally closed. So that's why that setting for the Eisenbud-Goto conjecture is still open. On the other hand, it is the defining equation of a domain, so it's a prime ideal and it's non-degenerate. So we get, and you should think of reaslike algebras as sort of like a machine, right? You plug in your favorite ideal, you get out a prime ideal that has invariants that are easy to compute in terms of the invariance of the ideal you plugged into this machine. So that's our main machine for getting counterexamples. So how do we get counterexamples? Well, you have to plug in just the right family of ideals. So we get counterexamples. We choose ideals with large regularity. In particular, so to get counterexamples, and perhaps the most famous ideals with large regularity are ideals defined by what are called the Meyer-Meyer construction. And my favorite version of this is due to G-Co, but I'll also say you should look at work of Beyer-Mumford and Beyer-Stillman, where there are different versions of these ideals. But Coe's version is nice. So he proved that for every integer r at least 1, there exists a graded ideal, not necessarily prime, say I sub r, which is generated by 22r minus 2 quadrics, so degree 2 polynomials, in a polynomial ring with 22r variables for which the regularity of the quotient, so let me call the polynomial ring SR mod IR, is bigger than 2 to the 2 to the r minus 1 minus 1. So this is doubly exponential behavior in regularity in terms of the number of generators and number of variables. And so what we do is you just take one of these ideals, plug into this machine, compute its reaslike algebra, and ask what are these invariants. So plugging into the reaslike algebra machine, we get a family of graded prime ideals, say P sub r, in ever larger polynomial rings. Let's call them T sub r. With, and using the previous theorem, we can actually write down all of these invariants. So in particular, the regularity is, well, it's the regularity of the ideal you plugged in plus 2 plus the sum of the degrees of the generator. So there were 22 r minus 2 quadrics, so that's 44 r minus 4. I don't really care about the rest. All I care is that this is at least doubly exponential. And whereas the degree, or the multiplicity, it's supposed to be 2 times the product of the degrees of the generators plus 1. So if they were all quadrics, I'm going to get something exponential with a base of 3, and there were 22r minus 2 such generators. And it's not hard to check that something that's doubly exponential is eventually bigger than something that is singly exponential. And in particular, if r is at least 10, the regularity is strictly larger than the degree, and that's where we get our counterexamples. Okay, so that's the overview of the construction of the counterexamples, but I said there was one problem, right? The problem was these rings we're constructing are graded but not standard graded. So let me talk about how we go about fixing that problem. This is something we ended up calling standardization. And this is the one part of the talk that's actually joint work with Paolo Montaro and Lance Miller, as we actually replaced something that Arena and I did in our original paper. So the problem here is that T sub r, these polynomial rings, this is not standard graded. And the solution is, well, you should think of this, it's like homogenization, but it's not quite the same thing. So let me do just a quick review of the more traditional homogenization that I think everyone should be used to. So how do you homogenize a potentially non-homogeneous polynomial? Well, let's say you've got your polynomial ring in n variables. What you have to do is you have to introduce a new variable, say x0. And anytime you have a polynomial, which you don't assume is homogeneous, and let's say it's a bunch of coefficients ci times monomials mi, what you should do is you should multiply each monomial by the appropriate power of x0 to make it graded, or make it homogeneous. So this is a sum ci mi times x0 to the degree of the whole polynomial minus the degree of that monomial. And so I'm going to call this f prime. So f prime is what we're calling the homogenization of f. And okay, so that's how you homogenize a given polynomial. How do you homogenize an ideal? So given an ideal I inside of S, its homogenization is I prime, which is just the ideal generated by all of these homogenizations of elements from your original ideal. This is now living inside the polynomial ring S prime. Notice in general, it's not always sufficient to homogenize the generators. You have to homogenize every ideal. It is sufficient to first compute a Grosvenor basis and then homogenize all of those. But by way of example, this will give us a good comparison for what's going on. Let's say I is the ideal generated by x1 squared minus x2, x1 cubed minus x3 in a 3-variable polynomial ring. If we homogenize, what you end up with is an ideal generated by 3 quadrics. Oops. Which you might recognize as the twisted cubic curve. The thing I want to point out here is a lot of things changed, right? Degrees of generators changed when I went from an ideal to its homogenization. The number of generators changed. Who knows what happened to the resolution? So this is not a terribly useful technique to force an ideal to be graded if I sort of lose all the information I had. So notice here that first, the degrees and number of generators change. And 2, if you really want to compute this, it's necessary to make a Grosvenor basis computation. Is needed in practice. So that's not very useful if I'm trying to create standard graded versions of things in which I already understood really well the defining equations and the resolution. So there was a version of homogenization that Arena and Pava and I came up with, which we called step-by-step homogenization. It was a little bit ad hoc and it has some disadvantages. So let me talk about a different version. It's called prime standardization, which is really inspired by something that Ananyan and Hochster noticed in their proof of Stillman's question, which is based on the notion of a prime sequence. So let me define this really quickly. So a sequence of elements, say G1 through GT in a polynomial ring over a field in some number of variables, is a prime sequence if first, well, they define a proper ideal, and second, S mod, the quotient of the first I elements in this sequence, is a domain. For all I from 1 to t. And so immediately you can see that, well, since each element is a non-zero element in S mod the previous ones, and the previous ones define a domain, each one of these is a non-zero divisor on S mod the previous one. So I get every prime sequence is a regular sequence. And conversely, a homogeneous regular sequence such that S mod G1 through GT is a domain is a prime sequence, as is, therefore, any permutation of G1 through GT. And so one of the useful facts that Ananyan and Hochster proved about prime sequences was that if G1 through GT is a homogeneous prime sequence in S, and we consider the ring, the subring of the polynomial ring generated by those polynomials, well, we know they're a regular sequence, so R is going to be isomorphic abstractly to a polynomial ring in T variables, but you can say a little bit more. So let's let I be some polynomial, some ideal inside this polynomial subring. This is a graded ideal. So first, the ideals I and its extension to the larger polynomial ring have the same graded Betti numbers. That really just follows because the extension from R to S is flat. The more interesting fact, though, is that if I is prime, so is IS. So for instance, this fails if say G1 was x squared, and I think of taking k adjoint x squared and thinking of that as a subring of k adjoint x. Clearly, this would fail if I didn't have this stronger assumption that G1 through GT was a prime sequence. And so I'm running out of time, so let me just say really quickly how this works in the example. What do you do to use this in reverse? You, instead of replacing, I'm not taking advantage of the fact that the original ring was non-standard graded. I should take advantage of that. And so what I should do is every time I see a variable, say of degree D, I should add a bunch of new variables, take something really general in those new variables of the appropriate degree, and replace that variable by this very general thing. And since I'm changing a degree D variable now to a degree D form in a whole bunch of degree 1 variables, I can make this standard graded. And this proposition tells me that I preserve the primeness and I preserve the resolution, which are the two big things I care about for constructing counterexamples. So I guess I'll just say for the idea, replace degree D variable with very general degree D form in many new degree 1 variables. And we can show that if you take enough new variables and you do this generally enough, they will define a prime sequence. And so you get something, you can take advantage of the Nanian-Hochster result. And in the last minute, let me just mention that we do have other counterexamples that avoid this construction. So for instance, if you take the following ideal, x cubed, y cubed, x squared, z1 to the d, xy, z1, z3 to the d minus 1, minus x2, x4 to the d minus 1, plus y squared, z2 to the d minus 1, and you take its reaslike algebra, you get counterexamples for D sufficiently large. And so this is at least a family of counterexamples that do not rely on the Meyer-Meyer construction, which a lot of people see as a bit opaque and difficult to get a handle on. This is an ideal in a 6-variable polynomial ring defined by 2 cubic pure powers and 1 more homogeneous form of degree D plus 2. So it's a very concrete thing. You can plug it into McCullough 2 and see what happens. And in particular, we also have counterexamples that define 3-dimensional varieties in P5. And that's minimal with regard to the examples we have. But I see I'm out of time, so I'll stop here and thank you for your attention.
Thank you, Jason. We will take questions now.
This is Anant here. Quick question.
Yeah.
Okay. So yeah, I don't know like if this makes sense or not, but is there some kind of a bound on the degree by using some function regularity?
You mean a reversed
Yeah,
inequality?
something like that. Yeah. Because based on the counterexamples, you see that regularity is shooting up very high and the degree stays not very high.
So you're asking for large degree and small regularity?
Yeah. Are there examples known? I don't know. Is it a very silly question? I'm not sure.
I haven't really thought about it. I mean, certainly the degree is always less than, say, the maximal degree of a minimal generator times the codimension if you're Cohen-McCullough, but that's, no, I mean, that's true in general.
Okay.
But in terms of regularity, that's a bit trickier. I don't know. I don't think I have a good answer for you.
Okay. Yeah, but by the way, the talk was
maybe by
fascinating.
next week I'll have something more coherent
Sure,
to say.
sure. Thanks. Yeah, but this was a fascinating talk.
Thanks.
Enjoyed it.
Yeah. Jason, the reaslike algebras, did they first appear in work of Hochster and Anianen?
No, so we defined them for the first time.
Okay.
They were implicitly defined in a very specific case in a paper due to Joseph Becker, but the example he cites as an example due to Hochster. And so the whole point there was they were trying to find an ideal with many generators, but of fixed Hilbert-Samuel multiplicity. So they had these family of ideals known to T.T. Moe that had fixed multiplicity in larger number generators. And so they sort of plug that into this machine and produce these ideals. But it was just one specific case. They didn't define what the defining ideals or the defining generators were or the resolution or anything else. It was just one specific example that we sort of generalized. And personally, I was interested in defining or saying anything about resolutions of prime ideals. I ran across this paper and just tossed some examples into McCullough too. And if you looked at a few of the Betty tables, you could instantly see there was some structure there that was really interesting. And so that was sort of how the whole project got started.
I see. So for which ideal they produce more like examples?
I don't remember exactly. If you go to our original paper, we reference exactly
so
what paper this comes from.
So the original examples of Moe were in powered series ring in 3 variables.
I believe so, yes.
And
so it was a local example, not a graded example, but it was the same idea.
Okay. I see. And of course, once you have this truncated Rees algebra, you could ask what happens if you go to, if you include the I square, T square, and have T cube.
Sure.
That's also a truncated Rees algebra.
So I've definitely thought about this. The problem is you lose all information about defining ideals and resolutions, because what you can say is that, okay, for a Rees algebra, we don't know the defining equations, but we do understand that the defining equations of the symmetric algebra are there. They're sort of the ones that are linear in these variables y1 through ym. And I'll explain next time what the defining equations of the Rees-like algebra look like. In essence, because I include the t squared, it somehow obscures and obstructs all the other higher degree generators that could have been in the defining equation for the Rees algebra. So as you replace t squared with t cubed and t to the fourth, you would slowly reveal other defining equations from the Rees algebra that may or may not be there in general. But the fact that there's a t squared there, it hides everything, which sort of removes all the difficulty in computing defining equations at Rees algebras. So all the good stuff I can say about the t squared scenario, I cannot say anymore, even for t cubed. Unless you tell me what the defining equations for the Rees algebra are, then I could.
I see. Okay. So Rees algebra is too complicated to deal with. That's what.
In general, yes.
Yeah.
Yes. And so the whole power of what we do is because I don't have to put any conditions on the ideal. Any ideal is good enough.
Mm-hmm. Okay. Are there any further questions?
Well, may I ask a question? It's Dumitru here.
Sure,
So,
go ahead.
Well, this technique of prime standardization that it's still on the screen. So,
Yes.
What is the idea behind it? I mean, it's the first time I see it, so it's not very clear to me how it came.
So I was going to go through an example, but I sort of ran out of time. But the idea would be if I go back to the twisted cubic example, like I had earlier, so you would have this example is actually homogeneous if I force the degrees of the variables to be 1, 2, and 3. So what I should do if I'm going to do this prime standardization is I should leave x1 alone since it's already degree 1, but I should replace x2 by something really general in new variables of degree 2. So say something like, maybe a product I equals 1 to 5. 5 is big enough, I'm sure. So that's something that's, say a product or a sum of a bunch of products of new variables of degree 1. So these are monomials of degree 2. And then the x1 cubed minus, now I need something of degree 3. So this should suffice. So I claim that this is good enough to produce a standard graded ideal that's still prime and still has the same graded Betti table that the original ideal has. So I claim it's really a fairly simple idea. And it's not at all the way Ananyan and Hoekstra were using it. They were sort of using it in reverse. They wanted to know something nice about R, but we're using the fact that we're sort of living in R and working backwards. And you might say this is sort of inefficient, right? I'm adding a whole bunch of new variables, but because the resolution doesn't change, you could then take advantage of like a Bertini theorem and cut down by a bunch of general linear forms. And so I don't really need this many variables in the end. I hope that was sort of understandable.
Yeah, thanks.
The whole point is I want to fix the fact that it's not standard graded, and this is one way to do it that preserves all the things that I liked about the original ideal.
Excuse me, may I ask a question?
Sure.
I am not sure. You mentioned that this conjecture may be true by adding some extra assumptions, right?
Mm-hmm. Sure.
Do you have any idea what kind of assumption will be useful to this conjecture still be valid?
So that was what I mentioned up here, right? So I'm suggesting that one of these 4 things might be good enough. So if it's smooth, if it's normal, if it's not necessarily normal but toric, or a singular surface, these are all the open cases that potentially it could still be true. And I know there are partial results, even for the non-normal toric setting. So there's a result of Pava and Sternfels that do the codimension 2 case. There's a different result where you have to assume an associated polytope is simplicial, but it's still open in general.
I see. Thank you.
Sure.
I want to ask a local question rather than a graded one.
Okay.
So take a regular local ring and take an ideal and look at R mod nth power of the ideal.
Okay.
And now construct the associated graded ring of maximal ideal. So want to know whether the regularity as a function of the power is well behaved.
I don't know off the top of my head.
Yeah. So, I mean, it becomes more and more complicated as you take the higher and higher powers.
Sure.
But could it be predicted what the regularity function is, or it could be again a similar answer that okay, it could be doubly exponential, or
Well, I mean, there are these results that say in a graded polynomial ring, if you take powers of an ideal, that function is eventually linear in the power.
Right.
So I guess I would expect something similar, but that's just a guess.
Mm-hmm. Okay. Yeah. Okay, so I don't see further questions. So thank you, Jason, for your very nice, interesting talk for our audience, and we shall meet next week again at the same time for more explanations about reaslike algebras. Yeah.
All right.
Thank
Well,
you
thank you
very
very
much.
much.
Yeah.
Thanks for everyone for attending.
Yeah, we'll close the meeting for today.
Bye.
Bye-bye.